of oil and gas, the true story, is no secret guarded by those who make a living with it. It's an open story, a fascinating one, perhaps too seldom told. It's an open-end epic, for all of the fields have not yet been discovered. At the turn of the century, the story of oil was often portrayed as the saga of the true American dream. Daring young men scraped together enough money to buy a desolate tract of earth and sink some pipe. After months of toil, when all appeared certainly lost, the grand gusher came in, drenching the jubilant roughnecks in the magnificent black gold. There was always success. In reality, the story was just a dream, for it omitted the failures, the dry holes, the spent effort. The mystique continued to surround oil, neglecting the facts that the reward of wealth came equal with the right to go broke, and many did. Though its origins were on land, today the story continues offshore in the oceans of the world. The search, perhaps somewhat adventurous, must be tempered with time, gigantic investment, careful study, and technical capabilities. For oil is not a commodity made in a factory. It is not a substance that can be legislated into being or created by an artist's brush. It's the result of millions of years of nature's work. And we are the victims of nature's capriciousness, because she has deposited her hydrocarbons randomly, by whim it might seem, in the calm, the hostile, the shallow, the deep, the cold, the hot environments of the earth. It's only in recent years that man has learned to read the clues nature has so discreetly placed as to the whereabouts of hydrocarbons. All generated and commercially produced hydrocarbons, from natural gas to crude oils and solid residues, are generally called petroleum. Petroleum is only found in or associated with sedimentary source rocks, which, as newly deposited sediments, contain an abundance of plant or animal remains. What actually took place many millions of years ago to change organic remains into complex and varied hydrocarbons is not really known. But evidence indicates that plant life is probably predominant as a basic contributor over animal life. And very little is known about how hydrocarbons travel through the earth. It is known, however, that this movement is aided by the presence of salt water and by compaction, or squeezing. To be recoverable, hydrocarbons must leave their disseminated and minuscule state in the fine-grained source rocks and move into porous sands, limestones, or fractured rocks, where they're concentrated and susceptible to being withdrawn through drilled holes. These accumulations are known as reservoirs. Hydrocarbons will continue to migrate in porous reservoirs until trapped by some subsurface barrier or until it escapes to the surface. Hydrocarbon reserves are found by studying rocks taken from an area or through measurements of magnetic or gravity forces, radiometric or electrical characteristics, or acoustic wave propagation. The acoustic, or seismic as it's called, is the predominant method for offshore exploration. Basically, it's a simple principle, initiating a sound wave at the surface and recording the elapsed time of echoes from the various reflecting rock strata. Intermittent recordings obtained along a line are processed into a continuous profile, which gives a graphic portrayal of those beds that generate reflections of the acoustic wave. In a general sense, the profile shows the rock layers and their deformation by folding, faulting, or piercement by salt or shale intrusions. By using a network of such profiles and following a specific reflection, a contour map of subsurface structure is constructed. Such a map indicates structural domes, anticlines, faults, and other features which could form traps for hydrocarbons. The recording boat pinpoints the surface position of each recording through known stations on shore or by using the Earth satellites. Potential drilling sites can therefore be relocated with accuracy. Before drilling an exploration test, the rights to the area must be legally acquired in the United States by a successful bid for the specific tract at an offshore lease sale. In foreign areas, rights are acquired from the appropriate national agency. In U.S. waters, it's necessary to conduct an archaeological survey of the sea floor to assure that unnatural obstructions such as prehistory cultural sites and wrecked ships are not present. Once the area is declared clear, the drilling contractor will come in with the necessary equipment. If the well is located in relatively shallow water, a jack-up drilling rig may be used. This vessel is floated to the site and its legs lowered so that it sits on the sea floor and only its drilling deck and equipment are above the waves. Because it actually sits on the sea floor, the depths in which it can be used are limited. In deeper waters, the drilling contractor must turn to drill ships or semi-submersible drilling barges. A drill ship is exactly that, a ship to house a drilling rig on its deck. The ship reaches the site, it is anchored in position, and carries out its drilling duties through its hull. Another common drilling vessel is the semi-submersible drilling barge. Displacing as much as 45,500 tons, it may equal a battleship in weight. To operate, it's moved into position and held in place by anchors. Then the hull is submerged so that part of the vessel sinks below the surface, with the drilling deck remaining above. Once the vessel is in position, preparations are begun for drilling. A conductor pipe, 26 to 30 inches in diameter, is driven 100 to 300 feet into the sea floor to hard resistance. A marine riser pipe is extended from the drilling vessel to the conductor pipe. Drilling then begins. The drill bit cuts a hole about 22 inches in diameter with the initial depth ranging from 1,000 to 2,000 feet. Into the hole, a 20-inch diameter pipe is lowered, then cement is forced around it. A blowout preventer system is installed to contain small accumulations of gas or oil that may be encountered in further drilling, and then the marine riser is replaced. Using a smaller bit, drilling is resumed. Now drilling mud becomes of utmost importance. This special mixture of clay, water, and chemical additives circulates through the drill pipe, cools and lubricates the rotating bit, and provides a downward pressure in the hole to equalize the upward pressure of oil and gas. Drilling can continue to depths of 10,000 feet or more before any quantity of hydrocarbons is found. During the drilling operation, core samples may be taken to obtain information on the exact nature of the strata through which the well has been drilled. The samples are obtained in one of two ways. A core barrel may be attached to the end of the drill pipe so that as the pipe turns, a sample of the strata is collected in the cylinder. Or projectiles may be fired into the wall of the hole at certain depths, penetrating the sides of the wall and return to the surface with the sample inside. Gas and oil are sometimes detected by analyzing the returned drilling mud. But because this is not always possible, an electric well log is taken to determine the precise depth and location of hydrocarbons. By lowering electrodes into the hole, the electrical properties of the different formations can be recorded. This device records the porous versus the non-porous formations and the electrical resistance of the formations. For example, sandstone saturated with salt water has a low resistance, but sandstone filled with oil and gas has a high resistance. In those zones where favorable conditions are indicated, drill stem tests will be conducted. Samples are taken from each zone and the pressure and flow rates monitored. If a discovery is made and it's determined that it will provide enough revenue to pay for further development plus yield a profit, then engineering studies will begin. These will determine the best and most economical ways to develop the accumulation. The discovery well is usually plugged and abandoned. A series of confirmation holes may then be drilled in other parts of the tract. Along with other data, the results of these holes will determine the extent of the producing area and the volume of oil and gas present. Up to this point, the time and costs involved may be quite high or fairly moderate. The rig and operating costs for drilling the test holes can run over $65,000 a day. The lease or concession costs for the area can vary from a few $100,000 to hundreds of millions of dollars. With all the information from test holes, engineering studies can begin to determine how to develop the field, the number of producing locations to be drilled, their spacing, the number of producing platforms to be installed, how the product is to be stored and transported to shore. It is at this point that J. Ray McDermott and Company enters the scene. The company begins with the design, fabrication, and installation of offshore structures for drilling and production. Then installs and buries pipelines to carry the well stream to onshore tank farms, offshore terminals, or single buoy mooring systems, and continues its role with processing plants. When specifications have been set, engineering work begins. Civil, mechanical, electrical, chemical, and instrumentation engineers are utilized for the various aspects of the project. Marine engineers calculate data necessary to launch and set offshore structures in place once fabricated. Draftsmen translate engineering calculations into technical pictures called drawings. An offshore structure, or platform as it's called, consists of a jacket pinned to the ocean floor by piling. On piling which extends above the water is placed a deck section. On this deck may be placed a drilling rig, production facilities, living quarters, or whatever may be required. Because offshore structures must first withstand the horizontal forces of winds up to hurricane velocity and waves as high as 100 feet or more, probing research must be done into the environmental requirements of the structure. The procedure might be simplified and hastened if each structure were like the one before, but such is not the case, for each structure is unique. From the drawings, fabrication begins. The time needed for the actual building of one of these structures varies from 4 to 12 months, depending on the size and complexity. These giants are as tall as skyscrapers, and like their on-land counterparts, construction is a step-by-step process. Tubular members are rolled. Patterns laid out. Steel cut. Each joint fitted into position and welded into place. The components of each structure are fabricated into the largest possible units that may be economically and expeditiously transported from the fabrication yard to the job site. Once the jacket is completed, it is pulled from the shore onto a barge that transports it to the offshore location. On location, the jacket is launched by sliding it off the barge into the sea. Then the jacket is made ready for uprighting and positioning by giant derrick barges. It's the jacket with piling driven through its legs that will absorb the forces of perpetual movement of the waters while supporting the deck sections and equipment set on top, above the ocean's reach. Today, several types of structures are in use, and each has its own particular function. The tender-type platform appears to be nothing more than an offshore drilling platform with a barge moored alongside. The barge is, in reality, a drilling tender and provides support such as living quarters, storage, drilling mud, and large mechanical components. This system is limited by environmental conditions. The larger self-contained platform attends itself in even the most hostile environments. All components necessary for day-to-day operations of the platform, along with living, storage, and operating areas, are contained on the structure. When a platform is used for drilling only, the well stream must be transported via pipeline to another facility for processing. Here, then, is where the production platform must be utilized. This self-contained unit will take the well stream from the reservoir, separate the oil, the natural gas, the water, and other minerals, and ready them for the trip to shore by marine pipelines. Today, with advanced design technology, our company has placed into service around the world combination drilling and production platforms. On these massive complexes, the drilling and production sequences take place simultaneously. Using this method of operation, companies save money and valuable time in the production process. Through directional drilling techniques, as many as 50 wells can be drilled from one platform. The contractor's connection does not end with the design, fabrication, and installation of the jacket and deck sections. Company engineers and technicians supervise every phase of the hookup procedures. On these facilities, every pipe, every wire, every switch must be joined, tested, and retested before the complex can be turned over to the customer and production begun. While the production platforms are being installed, pipe-laying barges are busy preparing the means of transporting the oil and gas ashore to other platforms or to loading and unloading facilities. Barges as long as 420 feet lay mile after mile of concrete-coated pipe onto the seafloor. The pipe, ranging in diameter up to 56 inches, is usually in 40-foot sections. These are joined by passing through as many as 7 welding stations on the barge. Each finished weld is then X-rayed to assure a flaw-free connection, and the newly welded area is coated for corrosion protection. It then goes off the end of the barge, guided by a support system called a stinger. This device ensures a correct curve while the pipe is descending, and thus keeps the pipe from excessive bending and possible buckling. During the laying process, divers descend into the waters to inspect the pipe and the stinger. The stinger provides the necessary support to gently lower the pipe at the proper angle to the bottom. When the line is complete to the platform, these divers will again descend for the riser installation. Rising from the pipeline on the sea floor and fastened to the structure, a riser is an extension to the piping system on an offshore production platform. It connects the production facilities with the subsea line. The pipeline does not simply rest on the sea floor, vulnerable to disruption. A pipe bury barge, or jet barge as it's known, will provide a trench in which the pipe will rest. The barge pulls a sled over the line to direct high-pressure air and water under it, thus creating a trench into which the pipe settles. The natural movement of the currents on the sea floor will cover it in the trench. The destination of these pipelines may vary. They may terminate at an offshore gathering station where the oil and gas is further separated and then transmitted through other lines to other points. They may terminate onshore where huge tank farms store the liquid hydrocarbons for distribution to refineries throughout the world. From the tank farm, distribution methods vary. Underground pipelines may carry the oil and natural gas to processing plants. Also, pipelines reaching from the tank farms back into the water will allow crude carriers to load and unload the oil for distribution to or from their global markets. These tankers will dock at either multi-berth terminals or at single buoy mooring systems. Tankers moored alongside permanent terminals load or unload through giant arms designed so that the rising or falling of the ship will not affect the connection. As an alternative to the terminals, the single buoy mooring systems are designed to accommodate tankers singularly. Tankers can couple with the SBMs in open seas. Yet even with the distribution, McDermott's involvement with energy continues. From huge onshore processing facilities designed and built by the company, the vital product is further readied for final application. From plants such as this will flow the materials needed for gasoline, motor oil, synthetic fabrics, plastics, asphalt, and the innumerable end products we derive from oil. From here, natural gas will find its way to the consuming areas of the world to provide clean energy to light our homes, cook our foods, dry our clothes, and become the feedstock of a myriad of petrochemical industries. Still, even at this point, when we have engineered, fabricated, and installed offshore drilling and production platforms, installed and buried pipelines, engineered and built onshore facilities, and tanker facilities, our role in the industry continues. Over the 30 to 40-year life of a field, maintenance will be required, additions to existing facilities will be made, and equipment alterations needed. The company will again be called on at these times for its services, both over and in the water. And years later, when a field is depleted and the last of the oil and gas extracted, it's the offshore contractor who shall return. Salvaging the giant structure, the company will remove the deck and equipment, take the jacket from the ocean floor, survey the bottom to ensure it's clean of debris, and direct its divers to verify this with a physical inspection of the site. Then and only then will McDermott close its roll with a well stream and leave no trace in the environment that for a while man and nature worked together to provide a better life for the world's peoples. The story of oil and gas is not limited to a few, but rather touches each of the estimated 24 million shareholders of the 6 largest oil companies, the uncounted stockholders of the smaller companies, service companies, and related industries, and the millions of petroleum workers and consumers around the world. It is not limited to the calm blue waters of the world, but rather wherever petroleum might be found, in the marshes, under treacherous seas, in ice-chocked Arctic regions, or beneath blistering equatorial sun. It's a story that encompasses all of us, for it is energy that is the prime ingredient for sustaining life and improving the lifestyle of every person.